We are now starting chapter 4, and in this chapter we will learn how to solve second order linear differential equations, and also maybe even higher than orders as well. So first thing we do here in section 4.1 is see how in real life or in application of this second order linear differential equation exists. So we will develop the equation of the spring mass system. So we are looking at a spring mass system with a damper here, and when the mass is at the starting position here, it's sitting like this, not moving, then we say it is in equilibrium position. But when it is moved, it is stretched and released. So in this direction, the spring tries to get the mass back onto its equilibrium position, and then the velocity and the momentum forces it to go the other direction, and then spring again tries to get it back to the equilibrium position, and so the oscillations start. Now when the mass starts moving, if we represent the position function at any time from the equilibrium point, we can use the second law of motion, F is equal to ma, where a is the acceleration, and it is, if you recall, it is the second derivative of the position function. So we have m d2y by dt2. Now when the mass is displaced from equilibrium position, the spring is stretched or compressed, and it exerts a force that resists the displacement. This force is directly proportional to the displacement y, and is given by Hooke's law, y is equal to F is equal to negative ky. Now the k here is the constant of proportionality, and it is known as the stiffness of the spring. So different springs will have a different k. The negative sign shows that the force acts in the opposite direction to the displacement. Now all mechanical systems often experience friction. So when the mass is moving, left and right, so it produces vibrational motion, and the force is proportional to velocity and acts opposite to displacement. So this force also acts opposite to this displacement because it tries to bring the mass to a stop. So we can call this force due to friction equal to negative by prime or negative b dy by dt, because dy by dt is the velocity of the spring. Other forces acting on the oscillator, maybe there are none. So we just combine them and call them external forces. So FEXT, that's how we will represent. Now when we combine all the forces, so all these forces, the spring force, the friction, and the external, they are acting against the force due to motion. So when we combine all of them, we get this equation that y double prime is equal to negative ky minus by prime plus f external. So now we can move these two terms on the left side, and we end up getting my double prime plus by prime plus ky is equal to f external. So if you note, this is the second order linear differential equation. So now we will see how we solve them. That is going to be in the next section. In this section, we will talk about different values of k and b and m, how they affect the motion of the spring.